Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we're going to begin our examination of numerical computation techniques that apply to ordinary differential equations, and we will specifically be looking at first-order ODEs and the Euler method in this particular lesson. So, if I can get my slides to advance, there we go. We can write differential equations in many ways, but if we're looking at just an ordinary differential equation, I can use the prime notation or I can use dy dx for my first order derivative. And if I have a function that I can write as y prime equals something that involves the x's and the y's, then that would be a first order ordinary differential equation. And in order to solve that, I'm going to need one condition on the y. We call it usually an initial condition. And then if I had second order or higher order, I simply am going to have things where I have functions of x and all of the various derivatives to y, and the highest derivative of y is the order of the differential equation. Now our goal for each of these is going to be to find the value of or a description of y that satisfies the differential equation. We can categorize these things in a lot of different ways, but the one that we need to do right now is the comparison of an initial value problem or a boundary value problem. An initial value problem is one where all of the conditions are specified at a single value of x. For a first order ordinary differential equation, it's always an initial value problem because you're only specifying one value. For higher order differential equation, if I have second order, I need to specify two conditions, and both of those would be specified at the same value of x for an initial value problem. A boundary value problem means that my conditions are specified at multiple values of x. So in this particular case that I've shown here, we've got one is at x equals 0 and one is at x equal L. So maybe I'm looking at heat transfer along a beam or some sort of two-dimensional length. And so I'm just concerned about what the temperatures are perhaps at the two endpoints. And these are going to be called boundary value problems. And we need to know this because the solution technique depends on whether or not it's an IVP, an initial value problem, or a BVP, a boundary value problem. We're going to first look at the Euler method, which is a method that works for initial value problems, for IVPs. And logically, this one makes so much sense. We're just going to simply replace the dy dx with a really straightforward forward difference representation, the easiest one we've got. So y of x plus delta x minus y of x over delta x is going to be this function of my y and my x. Now that delta x we're going to call the step size. If I take this and solve for the y of x plus delta x, then I get the expression at the bottom there. Now we're going to replace this, instead of putting the functional notation y of x plus delta x, we're going to use a subscripted notation saying it's y of I plus 1. So it's the ith value of x plus a delta x plus 1 delta x. And so by using this forward difference method, we get that y of I plus 1 is equal to y of I, so the y of x that I started with, plus delta x times the function evaluated at y and x. So that's the Euler method. To really understand this, you're going to need to see an example, but we're going to put that in the next lesson. So at this time, we're going to pause, and thank you very much for your time.